Hello everybody. This video is going to focus on the first half of chapter 4. I'm going to be stepping through the slides. Very important concepts in this chapter. You can see here from the listing of topics, we'll be looking at relational and logical operators, and that kind of gets wrapped up with learning about the concept of what a Boolean is. We also will be looking at decision statements. That's why the chapter is called Decisions. And decision statements in programming, usually the first thing that you learn is how to work with if statements. And then latter parts of the chapter, which will be in the subsequent video, will cover sections 4.3 and 4.4. So my goal here tonight is to try to get through the first half of chapter 4. It is an important chapter. And the one thing I do want to point out as we move into this chapter, when we first began this course and we learned our pseudocoding and our coding, we learned that things in programming languages happen in sequential steps. And we do this, and then we do this, and then we do this, and then our program's done. You know, that's typically how it works. Like you get some input, you do some processing, you do some output. But the reality is very often when you're writing a program, sometimes what you do is dependent on something else. So in order to make a decision in the program, in order, like which path of code do I follow, we have to concoct statements that basically determine the truth or validity of a condition. And then depending on whether it's true or false, we will branch off and go one way or the other. You know, do I stop for gas on the way home? My fuel gauge says empty, I better stop, right? That's a pretty easy thing. Fuel gauge empty, true, stop for gas. You know, fuel gauge full, you know, drive on. So that's kind of like the basic concept here. But in order for any sort of a decision to be made in programming, there's always some sort of a true or false statement that's being tested. So we're learning right now the second major type of problem-solving technique for solving any sort of logical problem. And just to kind of reiterate what those were, sequence, step-by-step, decision or selection, some people will call it, and then the third one is repetition, which we haven't learned yet, but that's when we're going to learn looping in subsequent chapters. So let's begin. All right, so one of the first topic areas here is talking about what we call relational and logical operators. And, you know, I look at the way the author proceeds on some of these materials, and, you know, and I'm always going to put my little caveats in there. I'm always hoping that you guys sit down with the book that you paid a lot of money for. These books are not cheap, and that you take it to heart that you should read the book and read what the author has to say. This guy does write a very good textbook. But sometimes like the logic he uses in presenting the material might not match up with my logic. Like, why is he presenting this now? And actually some of the first few slides in the slideshow are kind of that nature, but I'm hoping to maybe clarify why he's doing it. And I also like to kind of point out, you know, like, this is what the book says, this is what they say you should do, but in reality, this is what I do. You know, the practical programmers, and you'll get that from a lot of people too, but I do want you to have all those bases covered. All right, so when it comes down to relational and logical operators, we're going to be looking at all these different bullet points here, so all these will break down into separate slides. So why don't we go ahead and just jump down to this first slide here of real content and talk about what we will call condition. Now, the reason we use the word condition is basically a condition in programming is a way that we create some sort of a statement that allows us to test that statement whether it's true or false. So for example, if I go back to like, am I out of gasoline, right? I might actually say that, and if I were to type a condition statement, I would say gasoline tank empty, or is the gasoline tank empty? Well, if I ask a question, then it asks you to answer it. But really what I should be saying is gas tank empty, true or false? Or maybe gas tank maybe less than 1/8 full. That's when you know, is your gas gauge coming on? True or false? Right? Well, if my gas gauge thing that says warning is on, it's a good chance I probably need to stop and get some gas. All right, so that's the way we're thinking. We're trying to create statements in programming that can easily be evaluated to true or false. Yes or no. Right or wrong. Okay, 1 or 0. Now, any sort of a condition, any sort of a statement that we ask that kind of a question where the result can only be true or false, those are called Boolean expressions. And Boolean is just a different way to say true or false. It also corresponds to a data type inside of all programming languages. All programming languages will have some sort of a provision for Boolean data types. And the only values that can be put into those data types would be the value true or false. All right, let's move on to the next slide. And this one, I look at, how this author proceeds, and I think it's kind of an interesting place to place this kind of information. Because I wouldn't necessarily go here, but the reason he's doing it is to kind of show you some concepts. All right, when it comes to any of the information that's generated by our computer, every time we sit down at that keyboard and we press a key on the keyboard, the key in the keyboard generates a series of electronic pulses of positive and negative voltages. Positive voltages represent 1s, negative voltages represent 0s. So every time I press a key on the keyboard, like the space bar actually puts out a series of electronic pulses that equate to the number 32. 32 is listed in a table of what we call our ANSI Character Set. There's also the ASCII Character Set, but in Windows we operate off the ANSI Character Set. So every time we press a key on the keyboard, and they have some examples here, and it could be letters, numbers, special symbols, but anytime you press a key, it generates electronic pulses. And when you generate those pulses from the keyboard, you can write statements that test to see which character is pressed. So was the enter key pressed, true or false? How do we test it? We check to see if those pulses that were sent out match up with the number. Now, of course, computers talk in 1s and 0s. They don't say 32. They'd probably say like 0110110 or something like that. So that's kind of an interesting thing. If you're curious about learning more about that, I often tell people that you can just Google, like, for example, ASCII key codes, something like this. And ASCII and ANSI are closely related. They're slightly different, but they're essentially the same. And you can see that somebody, probably some geek from way back when, created these tables. And what the tables do is they go through every character on the keyboard. I'm trying to look for one that's actually kind of clear. And for every thing that you can do on the keyboard, and sometimes way beyond what you can do on the keyboard, there are numeric codes. And those codes will often translate, there we go, to binary. And this isn't even the ones I'm looking for here. But ultimately, it all will translate to some sort of a binary code. Keyboard characters, every time you press one, the ASCII character set will generate a series of 8 binary digits. Every time you press the keyboard, 1 byte of information. 8 bits, 1 byte. So that's kind of interesting. Kind of a side note, or a footnote if you want. All right, so just to read what he's got on the slide, a numeric representation for every key on the keyboard and for other assorted characters. Why is that important? Because we can write computer code that tests for which key was pressed, right? Like when we put in those special character or those special access keys for when we were writing the stock sale program, we put the ampersand in front of something, what we're doing is we're triggering the operating system to say, hey, we're looking for this character code, so every time somebody hits the Alt key and presses that key, we can trigger off of that. And whether you realize it or not, in the background, there's kind of a true-false happening, right? And it's looking for those things running. All right, moving on to the next slide. So that when I say any character on the keyboard, Yes, but you know there's actually more characters that are possible from the character sets of your fonts than what appears on the keyboard. In some cases, you can actually trigger these by like pressing like Control Shift Alt G, for example, and it comes out with some weird character code. But that's important because you can actually use that to leverage output and to test for certain types of input. I think it's kind of odd how the author kind of places that slide at the beginning of chapter 4, but I do feel compelled to talk about it. He explains in more detail why he does it in the book, and I'll let you guys kind of suffice to that. But here's kind of the interesting thing. Why do we care? Because we can write code that tests for what keys are pressed. So in this case, he's showing that there's this thing like CHR with parentheses and an N. And what really is happening here is if I look at the very bottom of the screen and I see CHR 65, that's allowing me to take the character code for the capital letter A and write that into code. So that's one way I can kind of like make this correlation. Like if I'm testing for a certain key pressed, and it's not something I'm doing where it's an access key and throwing the ampersand in, I'm just allowing myself as a programmer to control it. Like, for example, in my Java class the other day, my second level Java class, we were writing these silly little graphic programs where we were moving a ball around the screen, right? And then you would use your arrow keys to move it around. And then one of the guys in class said, well, why don't we make it like all video games, so it's the WASD keys, right? Like most video games. And so I showed him how to do that, and that's basically how you do it. You read the character code, so every time the W is pressed, it looks for the character code associated with that, and then every time that's pressed, we have a trigger up or forward or whatever the case was. So we can actually program all the keys on the keyboard to react to the things that we are doing. There's also the capability of kind of taking that process in reverse, and this is kind of interesting, where I can take the character that I'm looking for and then convert it into the number code that goes with it. And that's kind of odd. Now, why on earth would you do that? Well, it depends on which direction you're going. If you're telling the machine to react to the key code, or if you're having the key code do output to the screen. That's really kind of the thing there. I'm not going to spend too much more time on that. That's not critical. I will not test you on this information. So a little footnote there, no testing on that. All right. But something I will test you on, and this is where we get into, really true logical operations. You guys, last week we talked about chapter 3, and we learned all about numeric data types, and we learned about all the different types of mathematical things that we could do, like addition, subtraction, multiplication, division, and then the weird ones like modulus division, right, where you just get the remainder, or where you take the divide sign, instead of forward slash, it's backslash, and it's integer division, where you get the whole number without the remainder. Two weird ones. Well, those are fine for doing math, but when we want to test things whether they're true or not, often we need to do comparisons. So for example, if I was writing my gasoline program and I need to know, should I stop for gas, I might write a little statement that says, if gas level is less than 1/8 of a tank, stop for gas, right? But I would be checking to see if it's true or not. So how would I write a statement like that? I would need some sort of a comparison operator. So if I might have a statement, just using the very first example, the less than symbol, where if I say gas level is less than 1/8 of a tank, stop for gas before you run out of gas, fool, right? All right, so we use these comparison operators very often when we're testing truth, and that's why they're included here. Because very often we're looking to see it, does something equal something? Does something not equal something? Does something less than or equal to or whatever? So these are the symbols, and you're probably familiar with the symbols from doing regular mathematics. But if you've come from a straight up math world, very often when we write less than or equal to, they do that with like a dash underneath the sign. But in programming, when we do less than or equal to, it's written like this, less than, and then the equal sign follows. These are only used for comparison. So in other words, unlike the assignment operator, which is just the equal sign, and this is kind of weird, because in most programming languages, we do this. And I want to make special note of that one. Visual Basic is an oddball language, folks. If I was doing this in Java, I wanted to test to see if one thing is equal to something else. I use two equal signs. And in Visual Basic, you can use two equal signs like other languages, but by default, the language does this. Now, this creates kind of a little bit of a logical confusion for students. Other languages will choose one single equal sign because that is used for assignment statements only. And what that means is the thing on the left gets the value of the thing on the right. Then when you want to check to see is x equal to y, to see if that's true or false, in other languages you would use two equal signs to do that. Nothing is getting assigned a value. Unfortunately, Visual Basic is one of these really quirky languages, and it allows us to use a single equal sign in true-false statements that does not assign values. You got to be very, very careful with that. The place where you would use that is inside an if statement, which we're about to learn, or a switch statement, which we're going to learn also. Okay? I'll show you when we get there. The nice thing is that with the modern versions of Visual Basic, you can now use the same language standards that you use in Java, for example, where you would use the two equal sign. And what I actually will recommend to you from a programming standpoint when you start to learn other languages is to use the double equal sign instead. Believe it or not, there's also a triple equal sign, but we'll do that one later, okay? All right, but just pay attention to those. Another oddball feature of Visual Basic is the not equal to. Notice how they do not equal to? They put a less than and a greater than right next to each other. That's the only language I know of that does it. You know how we do it in other languages? We just do this. Java, JavaScript, C#, C, C++, Python, blah, blah. Every language I can think of, they do it like that. Exclamation equal. So if you do know another language and you're coming into Visual Basic fresh, this is an oddball, and I always try to point it out because it's critical. All right. Going back to this concept of a condition. Is this being repeated? It sure is. Condition is an expression involving relational and or logical operators. The ones that we just looked at on the previous slide, those are relational operators. Is something equal to something else? Is it less than something else? Less than or equal to? How do they relate to each other? Okay? So that's why we call them relational operators. There is the other type, the logical operators. We're going to see that a few slides down. And that's when we start to apply multiple conditions to situations. And I'll show you how that works. Remember, the evaluation of any relational statement is going to be true or false. So what we have coming up next here is a series of slides that kind of put some scenarios up there that will have you kind of guess as to what's going on. Now, normally, if I was like a traditional PowerPoint person, where I'd run it in slideshow mode, the thing would pop up and the stuff would kind of be hidden at the bottom. So try to kind of block that out of your mind if you can. But it says here, if A equals 3 and B equals 4, we would evaluate a statement like this. So what we have here is a statement. Notice there's no equal sign here. We just have a bunch of math going on. On the left side, A is 3, right? So A is 3 and B is 4. A plus B is going to equal 7. On the other side of the relational operator, we have 2 times A. What's A? A is 3, see? So 2 times 3 is 6. Is 7 less than 6? No. That statement is false. See how this is working? And then depending on if the statement is true or false, then we take different courses of action. That's the whole point of this, folks. Try another one. A is 4 and B is 3 and C is hello. C is a string, right? The others are numbers. The first statement says C dot length. What is the length of C? 5. H-E-L-L-O. 5 letters. The length is 5. So even though we're dealing with a string, we're running what they call a function on that string that counts how many letters. So all of a sudden, that's a number. Even though we're looking at a string, we're counting it. So it's 5 minus 2. Or excuse me, 5 minus 3, which equals 2. Does 2 equal 4 divided by 2? It sure does, right? So those are equal, so that statement is true. Okay. All right. So he's got a couple notes here. It says relational operators are binary. So if we're using, let's say, a less than sign or equal to or not equal to or whatever it happens to be, you have to have something on each side of that operator to test, right? You can't say is 1 less than nothing, right? You have to have something on both sides. So it always will evaluate to true or false. No other possible answers. Right. So anything that is expressed in that type of format, we call it a Boolean expression. Boolean is just a fancy way to say true or false. Check out this statement here. It says textbox.text equals CSTR. We didn't really talk about that yet. That's number conversions and string conversions, right? But when you're reading stuff in from a form and you have your option strict set to on, you will have to do this. You will have to convert from a number to a string. And what we're converting is 2 plus 3 less than 6. What's 2 plus 3? Is that less than 6? So the value is true, right? So we're going to convert true to a string. And so the text box.text, what will it display inside of it? The word true. Kind of interesting, right? There's no math there. Oh yeah, there is, but it's kind of behind the scenes. Interesting. All right, let's move on to the next slide. Now let's learn about some what we call logical operators. And here are the 3 most common. I will tell you that Visual Basic does have provisions for several others that I would call a little bit more advanced, but we start with these 3 basic ones because these are critical. Not is kind of interesting because basically what it says is the opposite of whatever you're saying. All right. So it makes a false expression true and vice versa. Now, I always have people say, why on earth would you do that? Well, there are certain times when you have certain expressions, it's easier to come up with the expression in the reverse and then negate it, in other words, flip it, rather than try to write it all in the negative. So for example, like if I was to write an equation that was like 1x plus y equals 7, as opposed to putting like negative number marks in front of everything and multiplying it by -1. That's just an example. All right, but let's skip that one and go to the second one. The ands and the ors are pretty critical to understand. Because sometimes we have situations where we're testing not one expression for true and false, but multiple ones. All right, so I'm driving home, and I look at my gas gauge, right? And I go, is gas less than 1/8 tank? True. And do I have enough money in my pocket to buy gas? False. All right, so what do? I keep driving and hope I make it home. So what I'm showing you is that for an and to work, an and requires that both of the statements are true. And actually, you can extend that. It doesn't have to be just both. It can be multiple ones. Do I have less than 1/8 tank of a gas? Do I have enough money in my pocket? I'm trying to think of a third scenario that would fit with that. Yeah. Is there a gas station on the way home? They all have to be true in order to work. So with an and, the condition is all of it has to be true for the whole thing to be true. All right? Or conversely, only requires that one of the statements is true for it all to be true. Okay, now I'm trying to follow like my gasoline example, and I'm not really sure I have one. How about, yeah, do I have cash or do you have your credit card? Either one being true that you can stop and get gas. That's a good one. Yeah, very, very much so. So just remember that. And all of it has to be true or only one has to be true. Not does the inverse and negates things. All right, let's look at some examples because I think the examples kind of help to make it resonate a little bit more. All right, so n equals 4. Answer, or ANSW, equals capital Y. Now, test the expressions. First, they're demonstrating not, which I don't like starting with nots in teaching, but that's what the author does, so let's just go with it. The way I would evaluate an expression like this is I would first look at what's inside, and I'd say, is n less than 6? It is. So the inside of it is true, but we're looking for not true, which means it's false. Got that? Okay. So the next one, answer equals y, or answer equals small y. True, because the first part is true. The second part is not, but only one has to be true for an or for the whole statement to be true. Got that? I know it's a little weird. Try the next one. Answer equals capital Y and answer equals lowercase y. Can't be both, folks. Right? So not both of them. It's a Hangout message if you're wondering. It's not both of them can be true, but an and requires that both of them are true. So the statement is false. Right? All right. All right, how about the bottom one? Answer equals lowercase y not. That is true. Because inside it's false, and if we negate it, it's true, so that's true. I know it's a little weird, right? But this is the kind of logic that we use to trigger decision statements. So we will write code that will look at scenarios. We might have ands and ors or nots in there. We might have multiple expressions tied together, and depending on how those evaluate to true or false, we trigger different code to execute. That's the whole point of this. So relational operators, the less than, greater than, equal to, all those. And then the logical operators are ands, ors, and nots. And just a reminder, Visual Basic has some others that are a little bit more advanced. And I don't worry about those so much because you can do most of your work with just regular ands and ors and call it a day. All right, moving on to the next thing. Visual Basic does have built into it as a primitive data type a Boolean. So notice this, the declaration, it says dim variable, whatever the variable is called, as Boolean. It can only be one of two things, true or false. All right, so look at their example. They declare a variable, dim bool variable as Boolean. So we gave it a name, we told it what kind of thing it can hold, true or false, but we did not assign a value to it yet. Does not have a value. Then the second statement, we say the Boolean variable is the result of 2 less than 6, and really this 2 less than 6 should really be kind of seen in this scenario as a question of sorts, right? Because is that statement true or false? That's true. So bool var then becomes true, and then if I convert that to text and put it in a text box, it would read true. The word true. Okay? Now, for those of you that remember your math, or maybe for those of you that choose to forget your math, right? When you learn regular mathematics, you also learn that you can write statements like this in math, where you can see if the number n, the unknown, sits in between 2 and 5. You can do it in a series like that. But you know what? That does not work in programming. In programming, we have to change the way that we do it. Programming will not evaluate this as one expression. We actually have to switch it to what they do on the next slide, which is to break it into two separate expressions, which is 2 less than n and is n less than 5. And if n is anything like 3 or 4, that will be true, right? If I put in the number 5, the first part is true, but the second part is not. So the statement becomes false. Okay? Now the reason that the author has these slides in here is because he knows that, many times when people are learning programming, and if you guys aren't seeing it yet, all the correlations between programming and mathematics, because there's a logic to mathematics, there's a system to mathematics, as there is with programming. And it doesn't mean if you're afraid of math, you should be afraid of programming, because that's not where your head should be. The beautiful thing about both programming and mathematics, you know what it is? It's got these really simple rules that we follow that don't change, right? People always hate learning math, but the reality is, coming from the standpoint where I've taught math, because it kind of goes with computer science, where I always love teaching math because you know what? They don't do upgrades to like division. There's not like, exponents 2.0. They don't upgrade the versions. The math is just always the math. It never changes. That's really kind of the thing I like about it. All right, but let's take a look at like what you might think of as, coming from the math world and how you might express things and how you would actually replace some of those concepts inside of a programming language. So in the first bullet, he says a common error is to replace the condition not 2 is less than 3 with the condition 2 is greater than 3. Now hold on a second. You think about this logically. We're saying in the first expression, we're checking to see is 2 less than 3. What does that evaluate to? True, right? But we're looking for the opposite of that, which means false. Now that does not mean, because in mathematics, when you start to negate things, you can flip signs. That doesn't happen in programming. We can't flip that less than to a greater than and have it mean the same thing. Because what's inside those parentheses is isolated. So 2 greater than 3 is false, like the top one is, but it doesn't mean the same thing. So that's a real important distinction. And what they're showing here is if you do want to negate it, what we're really truly saying is 2 greater than or equal to 3. Which is, okay, and I know this is a little bit of a head bender, and I really don't want to go into like mathematical proofs on it, but just important thing to note that some of the ways that we apply rules to math does not directly translate to programming languages, because there's a logical leap that happens when you switch to a programming language. More of an FYI than anything else. All right. Now, he's got an interesting little thing in here, and honestly, I kind of question why this slide is in here, honestly. But he talks about the expression, how we have a string variable, and you notice there's this little function here they call ends with a different string variable. So what they're really trying to tell you is that I have one string that might contain a different string, perhaps. So if I had like the word like pizza pie, so does my string pizza pie end with pie, like string 2? You see what I'm trying to say? And he basically is coming up with all the different scenarios here as to whether or not something is true or false. Once again, this is not something I'm testing you on, but he does an explanation as to how the technology works. So for the most part here, I would just say gloss over this slide, not being tested on it, and I don't expect you to write any code in this scenario. I always try to compare it to what he does in the book, but let's actually look at a tangible example, and you'll see what he's trying to shoot for, because I think the proof is in the pudding. It says, after the following code is executed, each text box will contain the word true. So we declare a string variable called first name with William, right? And then we check to see first name ends with AM. It sure does, right? So the result of that is true. That's what he's trying to demonstrate here. And then the second text box, he says, first name starts with Will. Does it? It sure does. That's true. So what he's showing you that you could actually write code that would test to see if a string begins with certain letters and ends with certain letters, and you can test for true and false based on that. Now, I think that's a simpler way to say it than trying to read through his last slide, where the language I thought was kind of convoluted. So I think that's kind of a neat example, but it does allow you to see if something contains something else. Once again, setting something to true and false. There's other Boolean expressions too that are kind of interesting, and this is a common one that we see in a lot of programming languages. Very often we check to see, well, if I need the user to input a number, right? How do I make sure that he inputted a number, right? So we have this thing called isNumeric. So the thing that I typed into the text field, is that a number? Well, I better check to see if it's a number before I try to do math with it, right? So that's kind of the reason for that. So looking at the examples at the bottom, it says isNumeric string 1, 2, 3. Yes, that's true because 1, 2, 3 really are numbers. So is it numeric? True. The second one, $1, 2, 3. Believe it or not, in Visual Basic, that evaluates to true. I'm going to tell you what, in other languages, it would not. Oddball. Okay, but this is something that you should know. The bottom one says 3 minus 2. That comes up as false. You know why? Because that's inside of a string. That's not going to do math. That's just text. So that's why it comes up as false. It's all text. As soon as you put any letters or characters in there, it will evaluate to false. The $sign is different. Visual Basic, depending on the mode you're operating in, option strict on or off, it will read that and understand that it's a monetary amount and work with it. Asterisks, triple asterisks with a bold highlight footnote. Other languages don't do this, folks. So be careful. Visual Basic is very forgiving. That's why it's a good beginning language, but when you move to like a strict language like Java or C++ or something like that, they are not forgiving. You have to be precise. All right, let's continue. Moving on to the next section. And here's where we first learn about if statements. Yay, I know. I have some people clapping in class, right? Because this is exciting. Because when we actually start to create decision statements in programming, if statements are the very first decision statements that we learn in programming. All right. Here the guy's calling them if blocks. And then we're going to learn about all these additional things. I don't anticipate getting all the way through all of these before I pause this video or end this video, but we'll get as far as we can. And then next week we'll continue the rest. All right, so if blocks. Let's begin by actually looking at a statement as it would be written in Visual Basic code. So in Visual Basic, we do this. We use the keyword if, and then notice we have a condition. That was the word we were talking about earlier. And then the statement then. And what's going to happen is we'll have a condition. If I have enough money in my pocket, then I will stop for gas. So that would be the action. So if this condition evaluates to true, we execute the code that comes up here. Else, or otherwise, if it's not true, we will do the second action. And then we put out a statement, end if, and we're done. Visual Basic, this is how we do it. But the if statement is a construct that exists in every programming language I can think of. The syntax will be slightly different, but the concept is exactly the same. We say if, we test a condition. If true, we execute it. Else, we execute something else. All right. Next thing he does is he shows us a different kind. Now notice the difference between this one and the previous one. This one does not have an else. Right? So this would be the scenario if I have, okay, if there is no gas station. No, that's not a good one. If there's a gas station, stop for gas. Otherwise, you just keep driving. You just move on to the next code. There's no else. There's no alternative action. You only do something if the condition is true. If it's not true, don't worry about it. Carry on. Move on to the next code. So now, which one do you use? Well, it depends on what you're doing. In some scenarios, you're going to have an either or. If this is true, do that. If this is not true, do that. Otherwise, if this is true, you do it. Otherwise, if it's not, don't worry about it. Keep going. That's the difference. How will you know? Well, when you're trying to solve a problem and you're thinking through it and you logic through the steps, the situation will present itself and make itself clear. And if not, and if it's not the right logic, you go to execute your code and run it, you'll see in the results, because you'll probably be expecting one thing to happen and something else happens, and that's when you know to adjust. But if you pseudocode well and you problem solve well, you'll have figured that out before you even get to the coding. And that's why you use pseudocode. It makes the coding easier. Now in terms of flowcharting and pseudocoding, he's got examples of both. And if you're pseudocoding, honestly, I would say that it's okay to write it in the form of an if statement, just like that. You can say, if discount percentage is greater than 50%, then break out the plastic and buy that TV set, right? Whatever the case may be. But in terms of the flow chart, the condition statement is placed inside of a diamond shape, and you state the condition. So, is the condition true? And then you branch yes or no. If it is true, do this. If it's not true, do that. This would be indicative of an if-else. because both sides, both the true side, the yes, and the no, both have programming actions that happen inside. So action 1 and action 2. He kind of has a little bit of an example here. So he's got two text fields, first number, second number, find the largest value, and then display the result. He comes up with some code. These are just examples to show you how it works. He begins by declaring a variable, num1, a second variable, num2, and a third variable, largest value. All are doubles. He allows you to type into the text field. It converts to a double. It gets stored in the variable. So he puts in the first number, puts in the second number. Then we have two numbers that we can check. And then we run the if statement. We say if num1 is greater than num2, then the largest value is num1, right? If num1 is bigger, that's the largest value. So now that really is how you name your variables. That's why it makes sense, is because he's named his variables well. Else, if the first one's not bigger, then the second one has to be bigger, right? Just logic. One's bigger than the other. Then num2 is the largest value. Then we can do an output statement at the bottom saying the largest value is whatever the largest value is. Kind of interesting. Now here's a little bit of a hint. There are some exercises that we do that ask you to put numbers in order. Isn't this weird? So if I take numbers and I sort them, this is what the computer's doing. Is this number bigger than that number? Okay, well if this one's bigger, this one's bigger. So if this one's bigger than that one's smaller, then I know which order they should go in. It's a very simple decision statement. All right. Then he shows the example output. First number, second number. Of course, the second number is bigger, so that's what displays. All right. So I like that he does that he gives you the concept, shows you the code, and then shows you how it looks in the form and how it runs. I also want to remind you, if you want to try this code, folks, just to play with, because some people are like that, whenever you see code like this, remember the ... what does that mean? There's a whole bunch of other code there. He just truncated it because he didn't want to put it all up on the screen. Don't type that in because that won't work. The way you come up with that code block is to put a button on the page and double click the button. It generates the code block, and then you can put all this code, all the in-between stuff in there. That'll work. Just to be clear. All right, on to slide number 30. All right, here's his example, second example. He says, how many gallons does a 10-gallon hat hold? Trick question. I can tell you it's not 10 gallons. All right, so they want you to evaluate this. Let's take a look at the code that he's writing to go with this. So basically, he's setting up a variable called answer, which is going to be a double, so it can hold decimal values. And then basically what you're going to do is you're going to type in an answer. What's your guess? Right? You'll probably put in 10. Right? And so he's setting that up so that it's grabbing whatever answer you typed up here in this little box, and it's storing it in answer. So you type in a number, it stores it. Then it tests the number, and it goes in the if statement. It says, if the answer is greater than or equal to 0.5, half a gallon, and the answer is less than or equal to 1 gallon, then you can output good. Right, so it's telling you a 10-gallon hat holds somewhere between a half gallon and a gallon. That's what it's telling you. Otherwise, the answer would be no. And then what he does is he kind of does this little thing where he takes the text, right? And it does an equal ampersand. Notice this is a clever little trick. He's got a text box called text solution, and into the text he's putting good, comma, space, and then gives you the rest of the answer. So in the output, it'll say, good, it holds about 3/4 of a gallon. No, it holds about 3/4, because you're probably going to type 10 in the first time. So that's kind of what he's doing. So he's setting up a scenario, but both of the answers, it has to be in the right range to say good. So chances are most people aren't going to guess 0.75 or 0.8 or something like that. They're probably going to guess 10 or 5 or something like that. Then he shows you the output. So if you type in 10, which is what you're likely to guess, it will come out with that answer. Okay, another example. All right, so this one is, do you know what the game of Skittles is? Yes or no? All right, so that's what our form is going to look like, and here's the code. For this one, we come up with a variable named MSG, message, we'll call it, as a string. Then he assigns to that variable a message. It says Skittles is an old form of bowling, concatenate, in which a wooden disc is used to knock, concatenate, down 9 pins arranged in the square. So that's all one long string. Now he tests. He goes, if txt answer, now keep in mind we're working off of this form right here. So if somebody types in an answer here, converted to uppercase equals n, so a person could type yes or no, uppercase or lowercase, right? How do they figure that out? Because we learned earlier, right, that every time you press a key, it has a certain key code. But what if the person have caps lock on, or they hold down the shift key and press Y uppercase or Y lowercase? I mean, we know what they mean, the same thing. So that's why we run this thing that converts it to uppercase. So if the person typed in a lowercase n, we convert it to upper, and then that's true, then we will show the message. Otherwise, what do? There's no else on this one. That's the trick here. There's no else. We only show the message if the person types an N. Because remember the question was, do you know what the game of Skittles is? And you know what? Most people don't know what the game of Skittles are. They know what the candy is, right? And then it says, life ain't all beer and Skittles. But if you type yes, you wouldn't need to know the answer. You see the conundrum there? So if you answered yes, it's like, well, you don't need the answer. But if you answered no, you want to know what it is, so that's when we're displaying it. So the person types no, and then we show the message on the screen. And what this does, this message box thing, we haven't learned this yet, it basically puts out a little box that looks like this that pops up in front of your application with a little OK. And this is what the result would be. So if you guys want to experiment with your code, a different way to send a message to a user is to use a message box that would display the message. And what that would output is this box, like that. Now we'll get to play with that when you actually use code. But if you want an alternative way to send a message to somebody, that would be it. So for example, if you were running a stock sale program and you wanted a person to enter a number of shares of stock, and you check to see is what they typed numeric, right? Remember the thing we just learned? Right? And it's not numeric, then you could put a message box up on the screen saying, hey, you're a complete idiot, you're supposed to type a number. Okay. And then they could go back and try to type a number in. So that's a scenario in which you could test that. And that was kind of answering the question that we were talking about here in class. All right. Moving on to the next concept here, slide number 37. We're looking at the concept of what we call nested if blocks. Do you know what a nested if block is? It's an if inside an if. All right. If I have less than an eighth of tank of gas left, right? If I have enough money, if there's a gas station along the way, you see how that's like all piecing together? How they're all becoming ifs inside of ifs? That's really kind of the whole concept here, and that's what we call a nested if. And to demonstrate this concept, what he's doing is he's creating a little example application, cost and revenue and show financial status. So let's see what code he's writing to go with that. So here's an example. He's saying if costs equal revenue, right, and we're thinking like basic business terms here. So if you're running a business and let's say you're selling coffee it costs you $1 to get that coffee to a customer, but the customer comes in and just gives you $1, how much revenue are you making? Or how much profit are you making? None. If your costs equal the amount of money you're pulling in, there's no profit. So you're breaking even. So if costs equal revenue, it's break even. Else, notice the terminology here, else, if costs are less than revenue, and think about the logic that goes here with this, folks. Because if costs equal revenue, you're breaking even, there's no other scenario that's possible, right? We're thinking true and false here. But if those two are not equal, then it's possible that the costs are less than the revenue. That's the scenario we want, right? We want to have $1 investment in our coffee, but we want to be able to charge $2 for it, right? So the cost is less than the revenue. Profit becomes a positive number, and we are turning a profit. Don't worry about the output stuff. That's just all interesting. If you want to play with it, you can always drop it into Visual Studio. Otherwise, if you're not turning a profit, the only other scenario that's left, and I don't have to check for it, because I already got the one that's equal, and I already got the one where I'm making a profit, the only other possibility is that my revenue is less than my cost, which is not the scenario you want in business. That means you're losing money. Notice I don't have to say else if again. I don't need to test it because the only other possible logical scenario is that you're losing money. So you see how that works? But we call this a nested if block because basically it's a whole if-else statement that sits inside of an else. It could also sit inside the top part. It just depends on the scenario that you're building. So when you have more complicated decision statements, like, if I have less than an eighth tank of gas, if I have money in my pocket, or if I have my credit card, so you come up with all these scenarios, and those scenarios will dictate how you put these together and come up with your conclusions. All right, so if you want to look at an example output from that, the costs are $9,500 and the revenue is $8,000, you're losing money. The scenario that you fell into on this slide is it wasn't up here, cost was not equal to revenue, cost was not less than revenue, so we end up obligatorily in the second else, and the output says it's a loss. It does calculate it. All right. Another way to handle these scenarios now, this is a little different. Now we're not nesting an if inside of an if. We actually are writing a different statement, and notice it kind of follows the pattern of the first one, but these are called else ifs, and notice there's no space in it this time. They are one keyword. And what happens is we subsequently check multiple conditions. So we check the first condition. If that's true, we do it. Check another condition. If that's true, we do it. Check another condition. If that's true, we do it. These are all different conditions that we're meeting. And then finally, we're also putting in kind of basically a fallback. If none of the conditions are true, then we just do the fourth one. All right, doing that in terms of our example form. Remember, find the largest value. Let's take a look at the code he's writing. This is kind of the same as what we did before. Two number variables, both are doubles. We allow the user to enter the values from the form. They get stored, and then we do comparisons. And what we're doing first is we're checking to see is the first number greater than the second number. If it happens to be, then we say, hey, the largest value is the second number greater than the first number? And notice else if, because if the first one's not true, then we can check the other scenario, which is the second number bigger. And if that's the case, then we say the second number's bigger. Otherwise, what's the alternative? If one's not bigger than the other, and the other one's not bigger than the other, the only thing that's left is that they're equal. I don't have to test for that scenario because that's the only logical thing that's left. So you see the logic that's going on here? And I know there's a little bit of repetition here, but the point here is this: we're checking the scenarios. And then once we check the scenarios, we can eliminate possibilities, and then we're left with the only thing that's left. All right. Moving on to our next example. This one's a little bit more complicated of an example. So the first thing that he does on this page is he sets up a bunch of variables. So I'm going to walk through this real slowly, and this will actually be the last thing we do in here tonight, is walk through this example, and we're going to be calling it a night, and then we'll pick up in the next video next week. All right, so he sets up a scenario here where he's got a couple of constants declared. One he's calling wage base as decimal. Looks like this person's making a decent amount of money, right? 118K, we could live with that, right? Guess what? As a talented programmer, you can easily expect to make that kind of money. That's why you want to be in programming, folks. The money's out there. Constant, Social Security rate. It says 0.062 as a decimal. All right. I'm not really sure what that means. It must be some sort of a multiplier. I know actually in my head that it is a multiplier. So they use it to do calculations off of your salary. And then there's a Medicare rate of 0.0145. Okay, whatever that means, it's some sort of a percentage apparently, or a multiplier that's given to us. Those are set as constants, meaning those are things that are not going to change in the program. Notice with the constants, if you remember this from last week, the constants, the convention, it's not a rule, the convention is that you name it in all uppercase. And that's a convention that most programmers follow in all languages. Constants cannot be changed. Remember that too. Next, we start to declare a bunch of different variables: year-to-date earnings, current earnings, total earnings, Social Security benefit tax, Medicare tax, FICA tax as decimal. Then apparently we have all those variables and we start to populate those. We pull a couple of things off of a form. We put them in year-to-date earnings, and then we put them in current earnings. Then we do a little bit of math with those. We add them together, and we come up with total earnings. On the next slide, we get to the if statement finally. And what I'll try to do is have that other slide at least a little bit visible there. We say if the total earnings are less than or equal to the wage base, that was 118,000, then we would calculate the Social Security benefit tax by just multiplying the rate times the current earnings. Otherwise, else if, test another condition here, those earnings, the year-to-date earnings, are less than the wage base, then we have a different calculation. There is no else for this. There's only those two scenarios that are being addressed. If neither scenario is addressed, then we do nothing. All right. So, and this is actually how they do calculate things. So, like when you start earning real money, you start paying real taxes. It kind of goes with it. And then all of a sudden it's like, okay, now I understand why people donate stuff to Goodwill and get a receipt. You know? Because it actually makes an impact on the amount of tax you pay. And they use different calculations. So if you ever hear somebody complaining about yeah, well, I get paid really well, but now I'm in a different tax bracket. And the first time you guys go out and you get a really decent paying job and you start to jump those tax brackets, you'll start to see it. And then you'll start to do things that hopefully minimize the amount of tax you're paying. And that's one of those calculations. So that goes on from there. There's more code, believe it or not. They do additional calculations, and then ultimately they do some based upon the tax that you've calculated in the previous slide, and then they compare that to a different tax rate to see if you're in the $200,000 range, right? Now that's some real money Right, folks? Yes, Mr. Kinnis. Then there's a different type of tax you pay altogether. All right, so he does calculations. If you're really curious about this one's actually not too bad to do when you get a chance. It's a fun one. If we had more time here in class, if I wanted to stretch out class a little bit longer, I would actually code this through for you because it's not that hard to build. But I think it's kind of fun to just look at it. So, the thing is if you earn more money, you pay different tax rates, and that's what this program basically does. How do they figure that out? Is they have certain calculations that they do. And when you fill out your tax returns, folks, you have all these complicated little forms that you do. They have this stuff all calculated out. So like if you put stuff in certain boxes on your tax form, then you do certain calculations. And if you check to see if it's less than this much or more than that much, it'll say it right on the tax form. So it's kind of interesting if you guys manually create your taxes. And I'm assuming that most of you at this rate probably do it electronically, which is what I would encourage you to do. Programs like TurboTax and the H&R Block one, when you download and install those pieces of software, what do you think they do? They have simple forms like this that are created that read the information in, and they just have complicated formulas in the background that go through and check all these conditions and scenarios, and depending on the numbers you type in, it gives you different results. So next time you use a program like that, you have some basis of comparison as to, at least a thought as to what's going on behind the scenes as we do that. Okay, just a couple more slides here. I thought I was about done, but just a couple more slides and then we'll break for the night. Let's go to slide number 49. And this one talks about input validation. So one thing that you might do at some point, remember I was talking about checking to see if something is a number before you run a block of code? Good programming will often test to see if user input is valid before you try to process the information that's added. Because if somebody types in a word where you're expecting the number, that can break your program. Especially if you turn option strict on. So a good way to do this is you can use a statement like this. So I can take a text box, check the text that's coming in from it, run it through the function called isNumeric. Is that a number? And if that's true, then I can do the math. Right? Smart thing to do. If it's not, then I got a problem. So that technique is one way that you can test it. Another real quick comment here is sometimes when you run into the scenario, if you're checking multiple conditions, and remember before when I was saying, if I have less than an eighth of a tank of gas, and if I have enough money in my pocket, and if there's a gas station along the way, I'll stop and get gas. But you can also write it if I have less than an eighth of a tank, and I have money in my pocket, and there's a station along the way, then I can go ahead and do the code. And in some situations, it's better to do the thing that's on the right because it's a clearer bit of code. It can get complicated at times when you write these complex AND statements or statements, but if you structure it right, it actually makes for much cleaner code than doing multiple ifs inside of each other. The thing on the right is preferred over the thing on the left, simply because it's cleaner. Some of that comes with a little bit of experience, and you'll pick that up as you go. You know, I'm not expecting you're going to be like an expert programmer within a couple of weeks here. That's not how it works. It takes time to learn those things. But just as a general rule, if you're finding yourself nesting your if statements, chances are you're better off writing it as conditions that are parts of an and or an or. All right, folks, that's it for tonight. Thank you for being a good audience, a good class, and we'll see you next time. This video ends here.